Okay, your sample integrative exercise. So it's all about acids and bases in this chapter, but here we are. Phosphorus acid, which we'll tell you right off the bat, just to give us a hint here, it's definitely a weak acid, has the Lewis structure shown here. Explain why H3PO3 is diprotic and not triprotic. Now don't forget, triprotic means 3 H ions are capable of being donated from this, although you know that as we move from H3PO3 to H2PO3, 1 minus, it becomes a weaker acid because the Ka dramatically starts to decrease. But in this case, they're saying it's diprotic. Well, let's see why based on composition here. So if we look at the structure, remember what makes acids a good acids is the fact that acids have to have polar HX bonds, right? So let's look at the O and H here. So obviously, between phosphorus and O, phosphorus is not a metal. Otherwise, this thing would act as a base. It would be the hydroxide ion. But in this case, because this is a covalent bond and the electronegativity of oxygen is 3.5, this is definitely a polar bond. And this is held on loosely here by a covalent bond. So this H ion is definitely donatable as a proton. And the same thing here, too. This bond is also polar, where in this case, this is held on loosely here. But what do you call it? There is a partial positive charge on hydrogen here, so this one can be lost easily as well. If you look up the electronegativity of phosphorus, now there's another H over here, but because they have pretty much the same electronegativity, I mean, you would categorize this as almost, or it is, nonpolar. So that H ion is not going to be pulled off. So a total of 1 and 2 ions can be pulled off. Hence, that's why, in this case, H3PO3 is diprotic, because that pH bond is nonpolar. Hence, H ion cannot dissociate from H3PO3. Okay, so for letter B, you got a 25 milliliter sample of this weak acid. It is titrated, which means a strong, a base of 0.012 molar concentration requires 23.3 milliliters to neutralize both acidic protons. So meaning we go from H3PO3 to HPO3, meaning you lose both protons. So what is the molarity of the H3PO3 solution? So the first thing we have to start with in letter B is the balanced equation of what's happening here. So you got your H3PO3, right? And they've added some sodium hydroxide, right? And we know that's going to titrate it, okay? And the products that you form will be obviously a salt and water. So I'm going to put water here, okay? And now they said that H3PO3 is going to lose both its acidic protons. So we're going to lose 2 of these protons from solution. And now it becomes HPO3 2 minus, right? Because now it's lost 2 protons. So the thing is, though, sodium, although a spectator, is going to react with that to form a aqueous salt. So you put these two together, Na plus 1 and HP3O2 minus, and you get yourself Na2PO3. Check to see if it's balanced. If not, add some coefficients. Okay, so you should have spotted 2 things that you have to do. You notice that there were 2 NAs there, so you got to put a 2 in front of NaOH, but that means you've also upset the amount of O's and H's, put a 2 in front of here, so it's a 1 to 2 ratio. Okay, so now it says, what is the molarity of the H3PO3 solution? So you know that the concentration of the base was 0.102 big M, and you know that it required 23.3 milliliters. From the molarity formula, you know that in this case, you got to convert that to liters, so that would just be 23.3 divided by 1,000, leaving us with 0.2 33 liters. And when you calculate for that, you get yourself, let me put it in a different color so we don't get confused. You get a small amount of moles, 2.38 times 10 to the negative third moles of NaOH. Okay, now we can do a little stoichiometry. We know that for every, for every 2 moles of NaOH that reacted, only 1 mole of H3PO3 reacted as well. And when you do that, remember, in a titration, it's not about molarity at all. In a titration, which we're going to talk more about in the next chapter, once you have equal moles of H ions, so pretty much equal moles of acid, which equals the moles of OH ions, you have completed your titration. Okay, so the amount of moles of H3PO3 you get here is 1.19, so it's pretty literally half the amount of moles formed. But you know that in this case, you have a 25 milliliter sample of H3PO3, so this is pretty easy then. If they're asking you what the molarity or concentration is, now you could set it up as big M equals 1.19 times 10 to the negative 3 moles of H3PO3 divided by 25 divided by 1,000, 0.025 liters, and you get a concentration of 0.0475 big M for H3PO3. Okay, so we talked a little about how weak acids, right, the more concentrated they become, the less percent, that's ionized in the solution. So we know that before it was titrated, it had a pH of 1.59. Calculate the percent ionized for the Ka1, which means the first association of H3PO3 into H2PO3, 1 minus. And they're assuming that Ka is much greater than Ka2. So you know what that pretty much means? That Ka2 here, yeah, the second association of H2PO3, 1 minus, is going to occur into HPO3, 2 minus, but it's such a small amount because the Ka is so little, it relies so heavily to the left. So what they're saying is we can calculate the percent ionization of Ka1, assuming that we don't even have to worry about calculating the amount of H ions in the second step in the deprotonization of this weak acid. So we're only going to look at it from this point on here, where I have H3PO3, right? And in this case, it will dissociate in a reversible equilibrium reaction where you form, as I said, H2PO3, 1 minus, because you lose the proton to solution, but you know that proton is the reason why the pH is low. So what we're going to have to do here then, if you want to find out percent ionization, you're going to need a ice box chart where, don't forget, you keep things that you need, keep things that you don't need. Now, I should have told you, obviously, that these are all aqueous in solution, so I think you have to keep everything here. Okay, so we know in this case, so in letter B, just don't forget, we calculated the concentration of the original H3PO3 solution was 0.0475, so I'm going to put that in a different color in our box. Okay. And they are telling you that the pH is 1.59 before adding any base. So we know if we get the antilog of the pH, negative pH, you can get the H ion concentration, right? So that's what I'm going to do here. Get the antilog using your calculator, and when you do that, you get roughly 0.026 molar, which makes sense because the pH is very low, so it should be a pretty big concentration of H ions. So that means, right, we started with 0 of this and 0 of that, where in this case, there is 0.026 molar change, and that means at equilibrium there is 0.026 molar hydrogen ions in solution. Same thing with the product of this anion now, but we know that this is the only thing that contributes to the pH. And so that means the change then, meaning we can then determine at equilibrium how much of this is left in concentration. If we know that 0.026 molar concentration is for the H ions, that means there's going to be some left over for H3PO3, and yes, there definitely will be, which is 0.0215 molar. So they want us to calculate Ka1, where in this case, remember, this is Ka1 going this way, right? Where in this case it loses the proton. So Ka1, which is what we're solving for, is always, right, the products ratio over the reactants. And now you can literally plug and chug. You can put your values in, and it should look something like this when you are done. Okay. And when you solve for this, you get a Ka, which, if done correctly, should be 0.031 or 3.1 times 10 to the negative 2, which means that Ka is not, I mean, it's weak, but it's actually pretty low. Or pretty high, actually, considering all the weak acids we talked about. Negative 2 is pretty low. And because it's greater than negative 5, make a guess. Because this is a much value greater than negative 5, so this Ka is a little bit higher than normal. Would we say the percent ionized would be less or more than 5%? So that's something that, you're going to calculate percent ionization anyway, but less or more than 5%. You could think about that for a moment before you watch the video. Okay, I'm hoping you decided that it'll be more than 5%, and it will be because the Ka is so low, so high, I keep getting confused, greater than negative 5, that it should be definitely over 5%. So the percent ionized, don't forget, the original solution of phosphorus acid was 0.0475 big M, and the amount that dissociated into H ion concentration, H ions, is 0.026 molar times 100. And when you do this with your calculator, you get roughly 55% ionized. And remember, there you go. So that's why our assumption is that. And don't forget, the reason why, even though you have weak acids that have very low pH, it has to do with the fact that, remember, weak acids can have low pHs, not just strong acids. It's because this concentration is so low. And because this concentration is pretty low, and yet the Ka is very high, pretty much, this numerator is very high because the amount of H ions that dissolved. Why? Because the Ka was rather larger for a weak acid, and because the concentration on the bottom wasn't so high but lower. So that's going to increase the percent ionized in solution. And so when you look at that graph, right, the percent ionized, right, we talked about over molar concentration, the more concentrated it is, I meant to say that the less concentrated it is at the beginning, the higher percent ionized. And that's the end of this sample grade integrative exercise.